Right, so last Tuesday, we introduced the concept of conditional variance of a random variable x with second moment, okay, given an arbitrary random variable y. Okay. And so there is a so-called conditional variance formula, and it is stated in proposition 7.5.2 in the textbook. Okay. So we let x be a random variable with finite second moment, and y an arbitrary random variable. Okay. Then we have the following conditional variance formula, okay, which say that the variance of x can be computed as a sum of two terms. The first is the variance of the expectation, the conditional expectation of the random variable x given random variable y, okay, plus the expectation of the conditional variance of x given y. So this formula, again, provides us an indirect way to find the variance of x. Okay, and it is obtained by first given a sign information we call random variable y. Okay, and so first of all, we find the conditional expectation of x given random variable y here. So this is a function of y. Okay, it's a function of y. And second, we find the conditional variance of x given y. So this again is a function of y again. Okay, it's a function of y. And then we take first of all, so they are function of y, and you know how to find the variance of the function of y, and also the expectation of function of y. Okay. All right, and so okay. So first of all, we know. So we have shown that the conditional variance of x given y is equal to the conditional expectation of x squared given random variable y minus the square of the conditional expectation of x given y. Okay, so we already showed that. Right? And so that this is, so when we take the variance is expectation, okay, the expectation of the conditional variance of x given y, then okay, minus the expectation of expectation. All right, and So that this is expectation of x squared minus expectation of the square of the conditional expectation of x given y. Okay. So this is the first case. Okay. Also, the variance of the conditional expectation of x given y, by definition, this is a random variable, right? So that this is the expectation of its square minus the square of its expectation. Okay? Right, because this is a random variable, right? So the variance of a random variable is the second moment of this random variable minus the square of its expectation. Okay? And so this is actually right, and the expectation is the expectation of x and the square. All right, and then you sum these two identity together. So that the variance of plus the expectation of the conditional variance of x given y. This is equal to the square minus the expectation of the square of the conditional expectation plus the expectation of this, right? And the minus, okay, and then you can cancel them, so that this is the second moment of x minus the square of the expectation of x, and so this is the variance of x, and we have done. Okay, so the proof is actually a simple proof, as you can see there. Any questions? Now we will consider an application of conditional expectation. Okay, in which we usually call the prediction. So conditional expectation and the prediction. Okay, so the scenario is here. A random variable x is observed, okay, and used, okay, right, so maybe we will say, all right, so a random variable, okay, maybe I will say, a random variable x is observed and used to predict another. Maybe I will change the role. Okay, so a random variable y is observed and used to predict another random variable x. Okay, all right. So x is unknown. Okay, so this one, unknown. Okay, and this one is known. Okay, because it's observed, so we know what is the value of the random variable y. Okay, and then we want to predict another random variable, the value of random variable x. Okay, and we know that random variable is a function of outcome, right? So different outcome gives you a different observed value, and use the observed value to predict the unknown value x of omega. Okay, so they are random variable because they are variable, which means that it depends on the outcome of your random experiment. Okay, so this is quite, and so, all right, and so the predictor, right, the predictor can be regarded, okay, as a data processing of the observed data. Y, i.e. g of y with some Borel measurable real valued function. G on R. Okay, so the situation is here. Okay, and so this is our random experiment. Okay, so this is the random experiments, and so we have an outcome omega. Okay, and now, all right. So there is a measurement device. X, okay, so the output x of omega, all right, and another measurement device, y, so this gives us, okay, and this value is observed. So this value is observed. All right, but we do not know the value of x for some reason. Okay, so we will want to use a predictor. So a predictor actually, we say it's a predictor, it's actually a data processing function. So it's G, okay, and so that the output would be, okay. And we want to, so that compare with, so here, so we want to compare, so that we want use this one to predict x, which means that we want the value is as close as to x as possible. Okay, so we need a measure. How close is it? We need a measure to that. Okay. All right, so a measure. So we want how can we find an optimal predictor okay, and what is the criterion of optimality? Okay, because when we say optimal, we have to have in a certain sense. Okay, so in here, all right. So there are quite a few important criteria, and in this section, we will consider one criterion. The criterion is to minimize the mean of the square of prediction error. Okay, so the prediction error, so we will say here, so we take the difference, the minus and the plus, to give us okay. So this is the prediction error. Okay, so that is the prediction error. And so which means that the prediction error is actually, again, a random variable. Okay, because it's the difference of two random variables. Right? We assume the predictor, the data pricing function, is Borel measurable. So g of y is a random variable. Okay, and the difference x minus g of y is again a random variable. And the mean of the square of the prediction error is just the second moment, right? The second moment of the prediction error. So, and we know if the second moment of the prediction error is 0, then by proposition 7.4 I think is C. Okay. Yeah. Point C, we know the prediction error equal to 0 with probability 1. So this is the best we can do, right? So that's why we use the mean of the square of the prediction error. Okay? Because if the mean of the square of the prediction error is 0, which means that the difference is equal to 0 with probability 1. So which means that the output of the predictor is equal to the unknown random variable x with probability 1. This is the best we can do in probability theory. Okay? So that's why the mean of the square of the prediction error is a good measure. Okay, it's a good measure for the goodness. All right, so we want to minimize. So we want to minimize that x minus g of y. Okay, so this is the prediction error, and we take the square of the prediction error and take the expectation. Okay, so. Oops, sorry. So this one is called the mean square error. Okay. So we want to minimize the mean square error. And the possible choice for the predictor G is any Fourier measurable function. So there are infinitely many possible choices, right? All right. And we want to find one which will minimize the mean square error. Can we do so? And the answer is yes, in principle, okay, which will be given in proposition 7.6.1. Now, for any data processing, right, so let x be a random variable with finite expectation. With finite second moment, I'm sorry. Okay, so let x be a random variable with finite second moment. And for any data processing, so for any data processing, G of y of an arbitrary variable y where G is a real measurable real valued function on R, we have the expectation of x minus gy square. Okay, so this is the mean square error. Has a low bound which is equal to x minus conditional expectation of x given y. Okay. So the lower bound is that if the data processing function is taken as a version of the conditional expectation of x given y, because this is a function of, okay, we know that this is of y, right? Okay, so we know this is a parametric function of y. Okay, so this is the lower bound of that, and equality holds if and only if that the g of x is equal to g of y is equal to the conditional expectation of x given y with probability 1. Okay. Right. It seems like we don't need x to have a finite sigmoid. Just expectation it would be enough. Okay. As you will see. All right, so let's see how to prove it. We first know that the mean square error, okay, for a data processing function G, okay, so the mean square error here is equal to, so we can xx minus plus square. Okay, so we subtract the conditional expectation of x given y, the existence is guaranteed by proposition 7.5.a because x is a random variable with finite expectation. Okay, so we subtract this conditional expectation of x given y and add the same random variable again, right? So, right. Okay, and so this difference become to the sum of two differences. Okay. All right, and so we have. Okay. Oh, let me see. Maybe here is the problem. Okay, so we have expectation. Okay, so we have here y minus expectation, the square term x minus expectation of x square right plus x y minus g of y square plus 2 times the x minus expectation of x given y times minus the difference, okay, and the expectation here. Okay. Oh. Okay. Okay. So right from here, we need yeah. So we need that it has finite. I'm sorry again. Finite second moment. Okay. Yeah. Because of here. So, for the existence of the expectation of this product, we need that this difference has finite second moment, and we also want this difference has finite second moment. All right. So. All right, x to be a random value with finite second moment, and also we need the g of y to have finite second moment. So I have to specify here. Such that g of y has finite second moment. Right. So we need that g of y has finite second moments. Right. We have. Okay. Right. So that we need that it has finite second moment, and the g of y also have finite second moment too. Okay. All right. Before we can apply linearity of expectation, so now since x has finite second moment, the conditional expectation of x given y has finite second moment. Okay. And also since g of y has finite second moment, and the x minus okay has finite second moment, right? And again, since g of y has finite second moment, this is by, let me say, by proposition 7.5.g we have proved before, and the difference has finite second moment. It's from okay 7.4.f. In this proposition, if two random variables have finite second moments, then they are linear combination. Okay, their linear combination has finite second moment. So this is the linear combination of two random variables. So this one has finite second moment, and this one has finite second moment. So the difference will have finite second moment by this proposition. Now, since g of y has finite second moment, so okay, so that has a finite second moment. All right, again by proposition 7.4.7, and the product of these two differences, okay, has finite expectation. By the Schwarz inequality, okay, so 7, the Schwarz inequality. D. I'm sorry, too near to the speaker. All right, so because this difference has finite second moment and this difference has finite second moment, so their product has finite expectation. Okay, so they have finite expectation by Schwarz inequality. Okay. All right, and so by proposition 7.5 point, the linearity, so which I think X, forgot the linearity, X, so they are okay, so the linearity of expectation in proposition 7.2.8. So we have that the expectation of x minus g of y square. Okay. So now we apply the linearity because this term, okay, this random value has expectation, this random variable has expectation, and this random value has expectation. Okay. So now we can apply the linearity of expectation. All right. So we have that x minus plus expectation of the second difference, plus 2 the expectation of the product of these two differences. Okay, now we have that, right? So this is the reason why we need x have finite second moment, and we also need that the data processing function g of y has finite second moment. Okay, so we have to check everything here before we can apply the linearity of expectation in proposition 7.2.8. Okay, now, so we will deal with this expectation first. Right. Now, right, but to evaluate that, a technique is that by conditioning on y. Okay, so we have, so to evaluate this expectation, we do it in 2 steps. We first conditioning on y. Okay. Right, so now we consider the conditional expectation of the product of the two differences. Okay, so we consider this one. Okay, and once we know this conditional expectation, we then take the expectation again. Okay, so So that to evaluate this expectation, we do it in 2 steps. Okay. Now, okay. All right. This one is a Fourier measurable function of y, right? So we can use the moving out property of conditional expectation. So we can move the vector out. Okay, so we have that. Right, we move it out and this difference here. Okay, this is with probability 1. So by the moving out property, in proposition 7.5.b. Okay, so this is by moving out property. And now here, look at this. Now we can apply the linearity of conditional expectation. Okay, so this is equal to so this is with probability 1. Okay, by the linearity of conditional expectation in proposition 7.5.e. Okay. Okay, now here. And again, we can use the moving out property because the conditional expectation of x given y is a function of y. Okay, so this is a function y, and your condition on y is actually, okay, you can move out. So that this is equal to minus expectation of, okay, and this is expectation of 1 given x. So this is a constant for a constant, then this is actually equal to 1. Okay. Okay. And so this is with probability 1 again. Again by the moving out property again here. Okay, maybe I use the red color here. So that this is equal to okay, and here is minus e with probability 1. Okay, and the difference is 0, so this is equal to 0 with probability 1. Okay, and so the expectation of the product of these two differences this is equal to and this is equal to 0. Okay. Because this conditional expectation is 0 with probability 1. And so this expectation is 0. It's quite surprising, right? It is quite surprising to know that this expectation is 0. Okay. Okay. Right. So, but if you compute the expectation by conditioning on y, then the result is not surprising. Okay. So now you can see the power of conditioning, because the conditioning is some sign information, and if you select a proper sign information, it will ease the computation of the expectation. Okay, and so now we have that the mean square error will be equal to the sum of two terms. One is the mean square error, okay, by using the conditional expectation of x given y as a data processing function of y. Okay, right. So this is, and also the second moment of the difference between the conditional expectation of x and y and the g of y. Okay, we have that. And because this term always non-negative, so that you have the lower bound. Okay, so you have this lower bound. And the equality holds if and only if the second moment of the differences is 0. Okay, if and only this is 0, and if only if that g of y is equal to the conditional expectation of x given y with probability 1 by proposition 7.4.c. Okay, we prove that exactly. Okay. All right, so we prove this fundamental proposition. Fundamental proposition. Okay. All right, so from proposition 7.6.1. The conditional expectation of x given y is the optimal predictor of x based on the observation of y. Okay. Under the mean square error. Criterion. Okay, so we actually answer our question. Under the mean square error criterion, the conditional expectation of x given y, okay, is the optimal predictor, okay, of x, of the unknown x, based on the observation of y. So the reason that's okay, so that this one is called the minimum mean square error, called the minimum mean square error, MMSE, okay, predictor of x based on y. Okay. So conditional expectation has this a strong interpretation, and it's very useful, okay, in engineering, because that it's quite often that in control or in communication, in many system theory that for example, in communications, the message we want to transmit is the input of certain channel, and then at the output of the certain channel, for example, if the channel is the air, okay, so we transmit messages through a radio of the air in the long distance, okay, and we receive a signal, right? So Y is the received signal, X is the message to transmit. So we don't know what is the message transmitted, right? Exact the message we don't, even though the message may be 0 or 1, only two values, but we don't know that it's 0 or 1, we don't know. All right, so X is the transmitted message, which is unknown. But Y is the received signal, and because we received that, so we know that. So we try to predict the input, the transmitted message based on the received signal. So that is the basics of the communication system. And every life in your cellular phone, that there are a lot of algorithms to do this kind of prediction. Okay, and you see that you can hear the voice of your parents, your relatives, your siblings, that the voice is so nice, and the voice is very clear. You know every message. Why? And also you can send a message on email. So, for example, I use Line, or you may use other kind of social media systems. And so they're so reliable. Why they are so reliable and in such a long distance? Such a long distance. So the basic idea is here, just like here. We have an algorithm and to do the best we can do. And here, in theory, we know the best we can do is the conditional expectation of the unknown transmitted message based on the received signal. Okay? And in the four special cases we considered in the previous section, for example, if x and y are both discrete type, or if x and y are jointly absolute continuous, or if one is continuous, the other is discrete. But the conditional random value is conditionally absolute continuous, all right? Given the discrete random value, if this is the cases, then you know how to compute the conditional expectation, right? A version of that. You don't know how to do that. If you know their joint distributions. Okay, so if you know the joint distribution between these two, okay, then no problem. You can compute the best predictor, which is the conditional expectation of x given y, if you know. But in many situations, it's hard to find the joint distribution between the unknown random variable and the known random variable you don't know. In this case, you are subject to some simpler predictor. Okay? Some simple predictor. One of the simple predictor is called the linear predictor. Okay, so this is best you can do, but you need more information. Okay, basically you should know the joint distribution between x and y. Okay. Okay, so that's to find we need the joint distribution of x and y. Right? In general. All right, and even the joint distribution of x and y is known. It may be intractable to compute the MMSE estimator or predictor G of y okay, so you may not know that. So we may want to know some simple predictor. So we set to the best linear predictor of x based on y can be obtained easily if the means and the variance of x and y and the correlation coefficients coefficient between x and y or no. Okay, so we'll see if we want to know the linear predictor, which means that the data processing function is a linear function of the observed data. Okay, so the G function, if we restrict ourselves for the G to be linear, okay, to be linear, then the best linear predictor as we will see, can be obtained if we know that the means and the variance of x and y, okay, and also the correlation coefficient between x and y. Okay, so before we proceed to find the best linear predictor, we take a break up to 2:30. right? Now, so we consider a generic linear predictor of x based on y, xg of y equal to a plus b y. Okay, so it's a linear function of the observed random variable. Okay. All right, and so to find, okay, so to find the linear MMSE, right, to minimize the mean square error, okay, we compute the mean square error right, so we define this as G of AB. So that is x minus a plus b y. Okay, so this is the mean squared error. Okay, the mean squared error, and so this becomes to be okay, as stated in proposition 7.6.1, require that the x has finite second moment, and for linear predictor to have second moment, we need y to have second moment. Right? So in this case, in the study of linear MMSE predictor, okay, we require that the x has second moment and y has second moment. Okay, so you can see that we need that, and because x and y has second moment, so the product x and y has finite expectation. Okay, so that everything is just fine here. Now we assume that the variance of y, or the observed data has variance bigger than 0. Why? Because if the variance of y is equal to 0, then y is a constant. Okay, y is a constant with per v1. So if the observed data is a constant with per v1, it's very hard, right, to predict okay, a general random variable x, right? So this is the basic requirement we need. Okay, right? So we assume that. Then, right? Then we study this mean square error. So it's a function of the parameter a and b. All right. So our job is to find the parameter which achieve the minimum mean square error under all possible linear predictor. Okay, and you can see this function is a quadratic function of the two parameters. Okay, as a quadratic function, we know that we will have it depends. See here, okay, because the coefficient here, all right, you can see. So this is a quadratic function with two variables. Okay, and this function is well studied in high school. Remember the conic section about, right? So this is the a quadratic function, right? And so you see that, and we will see it will have a minimum value. Okay. All right. So the technique here you can use the high school mathematics, or you can use the simple calculus you learn in the first semester in your freshman year. Okay, but first of all, we first see the first derivative, the partial derivative of g, and with respect to a, the first order partial derivative give us here. Okay, so here is just a simple argument. You should know that, okay, from high school or from your freshman year, and minus 2. Okay, so you have a linear function, okay, the gradient, and also for the second order partial derivatives, all right, so this is 2, they are 3, right? Second order partial derivative. Actually, you have 4, but because the mixed type, second order partial derivative are the same because they are continuous functions. So, okay, and actually they are constant. Give us. Okay, so you can see the. Because it's a quadratic function, so the second order partial derivatives are constants. Okay, they are constants there. Okay. Now, so look at the Hessian matrix. The Hessian matrix, all right, of a function is a matrix consisting of second order partial derivatives. As you know, the gradient vector consists of the first order partial derivatives. Okay, so now the Hessian matrix of G of AB is here. So the Hessian matrix, again, we have 2 parameters A and B. So the Hessian matrix okay, and you write down the Hessian matrix. You know this here. All right, so we have this Hessian matrix. Now, since the Hessian matrix is symmetric, of course, because the 2 mixed type second order partial derivatives are continuous, so they are equal, but actually they are constant here. And the determinant of the Hessian matrix, if you compute the determinant, you see this is equal to 4 of the minus here, the difference. And what is the difference? This is just the variance of y. So it's positive. All right, so you get a 2 by 2 matrix, which is symmetric, and the determinant is positive. So this is, okay. So that this is, so that AB is a positive definite. So it's a positive definite matrix. Okay, for all AB in R. Okay, so for arbitrary A and B, right? AB can be arbitrary, but the determinant of this Hessian matrix is a positive constant here, and so that it's a positive definite. Okay, the meaning of positive definite is that for any xy in the times the Hessian matrix. Okay, if you form the quadratic form here, this is always positive for all xy in R square minus 0 vector. Okay, this is called positive definite. Okay, the meaning of positive means that. Okay, so for any vector in the two-dimensional Euclidean space, when you get the quadratic form, it's always positive. Okay, now the gradient of the mean square error G of AB is 0 at is the 0 vector at AB equal to A0, B0, if and only if that the two linear, the two first order positive derivatives are zeros. All right, so you have to solve that minus 2 A0 plus 2 B0 expectation of y equal to 0, and minus 2 expectation of xy plus 2 A0 EY plus 2 B0 E of y square is 0. Okay, and so that we can solve that B0 is equal to okay, it's easy to solve them. Okay, this one, and so here, this is the covariance of x and y, and the denominator is the variance of y. Okay, and so that the B0, if we use the correlation coefficient between x and y, right here you get the ratio between the two standard deviations here. Okay. Okay, and then A0 becomes to be EX minus B 0 EY. Okay, so that this is equal to the mu of x minus rho of xy and sigma x, sigma y, and mu y here. This is A0. Okay. All right, so when A equal to A0 and B equal to B0 here, then with these two parameters, the gradient of the mean square error is 0. Okay. Now, by Taylor expansion, the mean square error can be expressed as here. So the GAB. Okay, so we expand this mean square error function because it's a quadratic function. Okay, so we can expand it about the point A0 and B0. Okay, and so that this is G of A0, B0, and plus because the gradient is 0, right? So this has become 2 factorial, A minus A0, B minus B0, and the Hessian matrix at A0, B0, and here A minus A0, B minus B0. Okay, here. Because the gradient is 0 already. Okay, so that it becomes 2. So this is a quadratic function. Okay, and so that this is greater than or equal to G of A0 and B0. Why? Because as we know, the Hessian matrix is positive definite. So you see the quadratic form always positive if the point xy is non-zero. Of course, if the point is 0 point, the quadratic form is 0, of course. Right? There's no problem. But if the point xy is non-zero, then the quadratic form is positive. Okay, so this is always positive, except that this is the 0 vector. All right, so we have lower bound, and the equality holds if and only if A equal to A0 and B equal to B0. Okay? So this is the lower bound. So this is the mean square error and has low bound. So this is the minimum mean square error we have. And the minimum mean square error can be achieved if A equal to A0 and B equal to B0. Okay? So the linear minimum mean square error, so MMSE predictor of X based on Y is here. It's G of Y. Okay, it's not. It's A 0 plus B0 Y, and so we apply here. So this is equal to mu x plus rho xy, and sigma x, sigma y, and y minus mu y. Okay. So this is our base linear predictor. Okay. So you see, in this linear predictor, we need the means of x, means of y. We need the variance, actually the standard deviation of x and y, and we also need the correlation coefficient of x and y here. Okay, and the mean square error of the LMMSE predictor is just g of A0, B0. And if you compute it, if you do the substitution, you find this is equal to the variance of the unknown variable x times 1 minus rho of xy square. Okay? Okay, and so you can see if the correlation coefficient is equal to plus 1 minus 1, which means that x and y are linearly related with probability 1. Okay, this is true if and only if x and y are linearly related. In this case, then the mean squared error of the LMMSE predictor, okay, becomes 0. So that we have a perfect predictor. Okay. So linear predictor, the best linear predictor is a perfect predictor, which means that the mean square error is 0 if and only if x and y are linearly related with probability 1, which means that the correlation coefficient is equal to plus 1 minus 1. Okay? So, and I think the recommended exercise, there are a couple, maybe one or a couple of estimators for you to find the best estimator, which are nonlinear. Okay, maybe the prediction function is a quadratic function of y. Okay, instead of linear function. Okay, so you can propose the degree of the predictor as a polynomial function, okay, and to find the best one, okay. But you may need more statistics from x and y. Any questions? Okay, so basically, to find the so-called the best of a group, a class of predictor, okay, you need optimization techniques. Okay, so you have to apply your knowledge on calculus, okay, to find them. Any questions? Okay. So the context here I presented quite engineering oriented. You see, it's become it's very useful. You know the prediction in engineering in economics or finance, you always need the so-called the best data processing function. Okay, for example, if you are in the finance sector, you may want to predict the price of a stock tomorrow, okay, or something like that. Then you may try your best to find it, okay. And so the problem may become to be very sophisticated because that in financial situation there's a lot of factors, okay. So that you not only one sign information observed data, because in here we just have only one observed data, but in many practical situations you may have 100 observed data. Okay, you have Y1, Y2, Y3, up to Y100 or Y1000. Alright? And use all this information to predict a price. Okay? Alright? And so if you have a lot of observed data, then the information, because it's a lot, so the size of the problem will become to be very big. Okay? But in principle, you can apply the same theory, but in computation, you need techniques to do so. Okay? So you apply the mathematical techniques you learned from calculus or from the other branches of mathematics to find, to solve the optimal problem here. But the formulation, the thinking, the way of thinking to see it is here, is from the probability theory. Okay, but I believe you already have enough foundation to do so. Okay, so in the future, if you find yourself to do this kind of optimal predictors in engineering, like in communications theory, or in systems, or control systems, or signal processing system, even in artificial intelligence or in machine learning area, there's a lot of problem about optimalities. And as you know, the factor you want to learn is random variables. Okay, there's a lot of data which is random by nature, so you have to actually think of it probabilistically. Okay, so any questions? Okay, so we have make efforts since the beginning of the semester, right? We build everything up to now. I believe you already have ability to deal with engineering problems now. Okay, and so now I have 2 sections to go in chapter 7. As I have said, chapter 7 is a long chapter from my point of view. Okay, it's because there are a lot of information I want to give to you, and so the last 2 sections contain important materials you can use later on. Okay, so I think I have some time to say something about the moment generating functions. So, all right, so 7.7 is about moment generating function. Moment generating function has the status as the Laplace transform in circuit theory, or in ordinary differential equations, or in signal system studies. All right? So if you have learned a Laplace transform or Fourier transform lots from other branches of mathematics, so you know they are very useful. So similarly, moment generating function is also useful, okay, in probability theory. All right, so let me define the moment generating function. M sub x of t of a random variable x, okay, is defined as here. It's actually the expectation of the exponential function of x, okay, exponential function, and the t is just a parameter. A parameter. So to find the expectation, okay, and this expectation always exists. Why? Because exponential function of x always positive valued. So this is a non-negative value random variable. As I defined in chapter 5, any non-negative random variable has expectation, maybe infinite, but the expectation always exists. Okay, so that so you actually, okay, so if you express it by the Riemann-Stieltjes integral, all right, so the integrator is the CDF of the random variable x here, okay? And the integrand is an exponential function of x. Now, there are two special cases. If x is discrete, then this is actually so if x is discrete, right? And so that the moment generating function is the sum, okay, of exponential. Okay, and the summation of x actually taking all the possible values, so it's countable. So this is, in general, this is a series sum only. Okay. The other is that if x is absolutely continuous, okay, then we can use a PDF of this random variable to evaluate that. And from here, you can see that the moment generating function is a Laplace transform of its PDF. Okay, so it's a Laplace transform of its PDF here. Okay. So this situation is quite general for you because a lot of random variable is absolutely continuous, so it has PDF. Okay, and so the evaluation of this one is actually a Laplace transform, but in general, for the discrete case, this is still, you can say that this is a kind of a Laplace transform you can have, but in the special kind things. All right, and for every real t, because we consider such that only real t, such that the expectation exists and is finite, because we want this become to a function of t, so that we need this is a real value, so it must be a finite value. Okay. Now, so there are some remarks before we go. The first one is that it is clear that the moment generating function is defined at t equal to 0. Why? If t equal to 0, this is 1. Okay? So expectation of 1 is equal to 1. Right? So always exists. So there is no question about that. The second thing, when t is extended to the complex variable z. Okay, so if we extend real t to complex z in the complex plane, so this one becomes to a function of complex variable. Okay, and yeah, we are lucky because in the last semester, okay, in the course of PDE and and the complex variable, we cover this case. The moment generating function comes to all right, so it becomes to the bilateral or two-sided Laplace transform. Oh, Laplace transform, you learned it in the second semester of the freshman year, right?
We are also learning it this semester in signals and systems.
That is Fourier transform.
No, we are studying Laplace transform.
Really? Yeah. In the course of PDE and the complex variable? Signal systems. Yeah, but you learn Laplace transform in ordinary ODE, right? In the second semester of the freshman year, right?
Except for the region of convergence.
Yeah, that's true. That's true. It's great. You have a lot of experience already. Okay, that's great. But I believe, okay, let me finish it. The Laplace transform of here, the Laplace transform of the CDF. Or sometimes call the generalized PDF of X, right? What do I mean generalized PDF? Okay, if X is absolutely continuous, okay, then of course you have a PDF right here, and a generalized PDF. Okay, see here. So you will have here. Let me see. Okay. Now, for the discrete case, let me address a little bit. For a discrete random variable, okay, x with AI, the set of possible values. Okay. Then a generalized PDF can be defined of x can be defined as here. Okay, and P of x AI and delta function of x minus AI. Okay, yeah. So we use the delta function. Okay, here I don't want to define what is the delta function. I believe it's the delta function you know when you learn, right? Because to define it precisely, it takes some time, okay? So I don't want to travel it. I just say, what do I mean the generalized here? Okay, and so in this case, now, if we use that, so here is, right, and okay, now I compute it. So this is okay here, and dx here. Now you evaluate that. All right, and assuming that the integration sign and the series sum can change their order, okay, so that this is equal to and the delta x minus AI dx. Okay, sum here. Okay, and P of x and a property of their function is here. You can first of all, because the sampling property of their function, the function of x becomes to EZAI and the delta of x minus AI dx here. Okay, all right, and so now right, and the integration of delta function equal to 1. So finally you get okay. So this is exactly equal to this sum here. Okay, because this one is okay. Okay, so I forgot. This is dx. Okay, so that this is the generalized probability density function, because you use generalized function, delta function here. Okay. All right. So, but usually a formal form is that this is a Laplace transform of the CDF. Okay. Because CDF will always exist for any random variables. Okay. So that we express it as the Riemann-Stieltjes integral here. Okay, and we call this as the Laplace transform of the integrator. This integrator is just a CDF. Okay, and look at this as a special cases. All right, so actually this is the Laplace transform in here. Okay, so let me finish it. And as we studied, the region of convergence we call ROC of this moment generating function as a function of complex variable is usually an open strip containing the imaginary axis in the complex plane. Okay, so usually in the complex plane, so this is the all right, so this is ROC. Okay, so this is C here. It's usually. So for every Z in here, in this open strip, right, the Laplace transform, this Laplace transform converge absolutely. Okay, so this is always exists there. And so now okay, so by the inverse bilateral Laplace transform, we can uniquely obtain the CDF or the generalized PDF of X from the moment generating function as here. Okay, so we can do the inverse Fourier transform if the line epsilon minus j infinity, epsilon plus j infinity, x contained in the ROC of the moment generating function. Okay. Right, so there is a one-to-one correspondence between the set of CDFs each of which has a moment generating function T defined on a neighborhood of the origin in R, and the set of their moment generating function. Okay. All right, so this is the later foundation of the theory of moment generating function. Why do we use the moment generating function? Because we have one-to-one correspondence. Okay, so to deal with the CDF or generalized density probability density function of a random variable, it's the same as to deal with the moment generating function. Okay, and we consider only those CDF such that their moment generating function is defined on the neighborhood of the origin. Okay, so we confine ourselves to those CDFs. Okay, and whose moment generating function is defined. If we use the real parameter t, then t will be the moment generating function is defined in a neighborhood, all right, of the origin 0. Okay, and the set of their moment generating function. So this is one-to-one correspondence. Okay, so once we know that the moment generating function of a certain CF, and we know that this moment generating function defined in a neighborhood of 0, then we know there is a unique corresponding CDF. Okay, we know that. Okay, so and in terms of that, so the study of the CDF can be moved to the study of the moment generating function, and in many situations you will see that the study of moment generating function is more convenient than the study of the CDF themselves. Okay, so that is the purpose of this section. All right, and so next week we will study some properties of the moment generating function and to give you the reason why it's called moment generating function. Okay, all right. So because that there are some preliminary mathematical requirements before the study, so I will send you a lecture notes for you to study before next Tuesday. That's okay, to expedite our discussion. Okay, because we have only 2 weeks left for the class lecture. Right. All right. So see you next Tuesday.